Well, hello everyone. I'm Dennis Helsel, and today's webinar is fitting distributions to data with Nondetects. We have a majority of the people that have registered are here now, so we're going to go ahead and start. I picked this first topic because it's one that's not fully spelled out in the book, the 2012 book on Nondetects and data analysis. So let's begin. First, I just want to let you know that there is this book from 2012 called Statistics for Censored Environmental Data Using Minitab and R, and there's a lot more information in the book than we're going to do today. So this is just one small piece of that. All right, well, then let's get started. I'm going to let you have a full screen of PowerPoint. So our topic is fitting distributions to data with Nondetects. And so I've already mentioned the book that has a lot more detail than today on handling data with Nondetects. The statistical name for data where you do not know a unique value for an observation, but you know that it's less than or greater than some threshold, like a detection limit, is called censored data. And so that's what we're talking about today, methods for censored data. Why would you want to fit a distribution to data? And the first reason is that you would compute summary statistics. So you would compute summary statistics for data that have a small number of observations. And one of the difficult things is that when you're trying to estimate extremes, like the highest values, something like upper percentiles, the 90th percentile or the 95th percentile, and you don't have very many observations, that's difficult to do, but you can model your data set with a distribution. And so if you're interested in a percentile like that, or maybe the UCL 95, an upper confidence limit on where the mean out in the real world might be, then with small numbers of observations, that's difficult. So my recommendation is when you have something like 8 to 20 observations that you would use a distribution to do that. And there's a long history of doing that in water resources, including flood studies and other things. You may also want to compare those statistics to a standard. And so again, getting a good estimate of the statistic itself is the best way to compare it to a standard to see if there's been an exceedance or not. So when you don't have much data to do that, it's hard to estimate things like the UCL 95 or the set of percentiles. So we would assume a model, a distribution for the shape of the data to project beyond perhaps where our data currently are. And that projection is only as good as the fit of the model to the shape of your data. And the problem is, with not a lot of observations, you don't know what the shape of your data is. So, but one thing I can tell you is that data in water resources and environmental data of a variety of kinds, air, water, soils, concentrations in biota, are skewed. And so something that does not fit very well to skewed data is a normal distribution. So if you've gone ahead and computed a UCL 95, let's say, or percentiles using a t-statistic, then that's assuming that you have a normal distribution. And it's not going to work as well as a better fitting distribution. If you had a larger data set, and my rule of thumb is about 20 observations, then you can start to do non-parametric estimates of what those statistics are, like the percentiles or the UCL 95. And I'll give you one quick example of that later today, even though it's not part of the topic. So one of the things that I've seen, observed, is that when you have a small amount of data, sometimes people, or sometimes even regulations or guidance documents, recommend using the maximum of the number of data that you currently have. And that's not a particularly good procedure. It would be much better to assume a distribution, at least a well-fitting distribution. Because with small data sets, there's a very high probability that those new observations, if you collect a few more, will exceed the current maximum that you have. And so the maximum is not a good estimate of what an upper percentile would be, and it very well may not be a good estimate of what the UCL 95 would be. So when you have, let's say, less than 8 observations, the maximum of that is still pretty likely to be more towards the center of the data than towards the upper end. So for example, you could compute the probability with you have 4 observations of getting the maximum, and what does that represent in a distribution. And it's very likely that that is an estimate of somewhere below the 60th percentile. So it's more likely that estimates with small numbers of observations, that the maximum is not going to be a good estimate of even the UCL 95, much less an upper percentile like the 95th percentile. It's much more likely that it estimates something more like the mean itself or the median. So with 8 to 20 observations, you could use a model, at least, of the shape of the data and be able to project better. So what model should you use? And that answer is the one that best fits your data. So how do you know that? If you don't have a lot of data, then it would be a good practice to perhaps look at distributions of data in nearby longer record stations, places where you have a lot more data, perhaps of the same parameter, the same chemical, and determine what that distribution is, and then use that distribution for your smaller data set. As I mentioned before, most environmental data in a variety of media are skewed, and that's because we usually measure things that have a lower bound of 0. So with a lower bound of 0, that forces skewness and means that a skewed distribution, such as the log-normal, the gamma, or the Weibull distribution, would do a better job of fitting than a normal distribution would. So we can use some methods, graphical methods, like a QQ plot, also called a probability plot, and goodness of fit statistics, some numerical measures that tell us how well that distribution fits the set of data that you have, to determine which distribution to use. And you can do those kinds of things with censored data with Nondetects as well. So this is an example of a QQ plot, also called a probability plot, and it plots the probability of being less than or equal to the data value for an observation. And so what we have here is the value for the observation, or in this case it's logarithm, on the y-axis, and on the x-axis is the probability of getting at that value or something less than that value. So this is the percentile. The x-axis is the percentile for that value. And Nondetects, as you might notice, are not plotted. You notice that there's this gap on the left side here. In fact, the first 30% of the data are not plotted. This is a simple data set with one detection limit. These things work fine for multiple detection limits as well. But just for illustration purposes, with one detection limit at 0.01, we have 30% of the data that are less than 0.01. We don't know their exact values, so we don't plot them. So they are not shown, but what they are represented by is the space here, the percentages that they possess in the data set. So this 30% means that the percentiles for all of the detected values, which are plotted as black dots here, are shown correctly. And the lowest detected value is a little bit above the 30th percentile. Also on a QQ plot or probability plot is a straight line that represents the distribution. This is a normal distribution. We're plotting logs, so we're checking to see if this data looks like a log normal distribution. And it fits pretty well in a straight line, except for that one upper point. Then there are fit statistics. One of them, probably the most commonly used one, is the probability plot correlation coefficient, which is just the correlation on this plot. It would be taking the correlation of the logs of atrazine concentrations here and correlating them with a linear scale, not this percentile scale, but a linear scale down here called normal quantiles. And you'll see some of the QQ plots later on that have that linear scale with normal quantiles. So that correlation coefficient, just Pearson's R correlation, is the probability plot correlation coefficient, and if data were exactly on the distribution line, it would have a correlation of 1. And these data are not that way. But they're not far from it. This PPCC is a 0.94 in essence. So this might be a reasonable fit. So this is the correct way to plot data with Nondetects on a probability plot, and you'll find routines to do this in sections of statistical software called survival analysis or censored data sections. And these plots were done in Minitab, one of the commercial packages that does this, and really all the commercial packages that you pay for have a section on survival analysis or censored data. So just some examples of things you should not do. First, delete the Nondetects. If you delete the Nondetects and then plot them on a standard QQ plot that's not in the section on censored data, but just a regular QQ plot, then the lowest value here is really should be at the 31st or 32nd percentile, but it's being put down here at about the 1st or 2nd or 3rd percentile. So all of the percentages are incorrect. And that means that visually it gives you an incorrect idea of what the distribution is. This is again plotted as a log normal distribution in the center. And this shows a curve, which would mean that it doesn't fit very well. In fact, it really does fit quite well to a log normal. But because you've chopped off the lower 30% of the data, this is really just judging whether the top 70% of your data set looks like a log normal distribution. And that's certainly the top 70% of any distribution is not going to look like its distribution at all. This is giving us another fit statistic called the Anderson-Darling statistic, and that's perhaps one of the most powerful and so best statistics to use. And again, it's available in these packages. And like any test for a distribution, the null hypothesis is that it is like that distribution. So when you have a small p-value here and reject that, it's saying this does not fit a log normal distribution, when in fact it really does. So throwing away Nondetects is not the right way to plot data or to test to see if the data fit that distribution. Substitution of artificial values, I usually call it fabrication, is also not a good method. So here I've put in a half the detection limit. What does that do? It gives you a straight line on a plot here because they're all at exactly the same value. It will give you a series of straight lines if you have multiple detection limits. And none of those look like the original data. The data would have been following this central line representing the log normal. And so the detected values are back to something close to what they should be plotted at. But this straight line is not. And so the low end is really not accurate, and an evaluation of whether it fits the log normal or not is not accurate because log normal or any other distributions don't have these flat straight lines in the data. We don't have data that are all exactly the same as each other in 30% of the values and all at the low end. So it leads you to choosing the wrong distribution and getting bad estimates for the percentiles, at least at the low end. And these kind of things may also affect the mean and UCL and not give you good estimates of that as well. So if you use the censored data or survival analysis methods in software, and again, this is from Minitab, you can do things like doing these QQ plots for different distributions and decide which ones fit the best. So here is, the PPCC, and we can see that the normal distribution has a value of 0.47. The log normal had that 939. So the log normal is much closer to being a straight line than the normal is, and it's a much better fit. So the normal distribution, the second best, looks like it's the Weibull distribution, which is another skewed distribution here. So you can let the software decide how good the fit is to these distributions and then decide to pick one of the best ones and use it in computing upper percentiles and the UCL 95. So I'm going to use a data set for the rest of this talk that are arsenic concentrations in groundwater, and I think it came from a US EPA publication a while back. There are 21 observations, so it's still a small-ish data set. It's not quite as small as I was saying before. I'm doing that on purpose so I can show you a bootstrap at the end, a non-parametric method. But we're going to be at still a range where it might be a good thing to fit a distribution to it. And we have, of those 21, 2/3 of them, 67%, are censored below one of 4 detection limits. So 14 of the 21 are censored. And here are the 4 detection limits at 0.5, and there's only one less than 0.5, a less than 2, a less than 3, and then 11 less than 4s. And our maximum is just up a little above 5, so that highest detection limit covers a lot of the range of the data. So there's still not a huge amount of information in this, and it'd be a good thing to fit a distribution to it. By the way, I'm going to do the rest of the work in R. That's the free software package, the openly available software package that is really about the world standard in statistics, and it is a modular package, so you're going to be adding in pieces of it in what they call packages. And the 3 I'm using that handle censored data, and there are more, but these are the 3 that I find most useful, are ENV stats, stands for environmental stats, the NADA package, and FitDistR Plus package, which will do a lot of the plotting procedures. So here's a box plot. Everything below 4 is really the result of fitting a distribution to it. A log normal is the default. Here is the box plot. The values above 4 are things that we can see because it's all the detects, but it would just be the upper end of this tail of the box plot. And so even to look at what a distribution of this might be, you could do a box plot assuming a distribution, which is what's done here. Another way is to show it with a CDF, a cumulative distribution function, and that's just the set of percentiles or quantiles, so that a value on the y-axis here of CDF of 0.5 is just an estimate of the median. The data are drawn with a step function, this black line, that's a step function, and so the median going on over to that would be, it looks like 1 point about 3 or 4 for this data. And then you can also show the distributions that might be fit to that. So here in the red or orange is a gamma distribution. That's a skewed distribution. Here's the log normal. Just above it, at least in the center, is a dashed green, it looks like, line to me. And the normal distribution is down below the dotted blue. And so this is 3 distributions fit to that. And it's visually certainly looks like the gamma and log normal fit better. The normal does not. And that's especially true when you look down towards the bottom, because the normal is projecting that some percentage of the data are below 0. So that's one problem, and one big problem with a normal distribution is that you can easily get data projected as being values as being negative. You may even get ends of confidence intervals, like the lower confidence limit on the mean at times being negative. And that's not realistic at all. And so that's going to show up as a bad fit to the data. So we're going to fit data like those curves using something called maximum likelihood. There are other methods to do it. This is one of the standard ones. And what maximum likelihood does, I won't go into the math today, is to start with the observed data and then your statement of which distribution should be used. So you're saying, I want to fit a log normal, I want to fit a gamma, etc. And then it will provide the best fit for that type of distribution by tweaking the values for the parameters, things like the mean and standard deviation for the distribution. And that tweaking is done with an optimization procedure to maximize the match between the observed data and those parameters. So which set of parameters is most likely to have produced the data that you have seen. And for censored data, it can do that matching computing percentiles for the detected values, because you know what those values are, and then using the information that you do have about non-detects, the observed proportion of data, both detects and non-detects, that are occurring below each detection limit. So it's going to look at the proportion of data below 4 in this case, and there are some detected data below 4 when the detection limits were lower, and then counting the number of non-detects that are below 4, all the less than 4s, then the less than 3s, less than 2s, less than 0.5s. So you know what proportion of data are below each detection limit, and that proportional information is what is used to represent the information that the non-detects have. And so here is that fit for the gamma distribution, and it's fitting the data to it's fitting this curve and the parameters for the curve to the step function, the detects that we have. Its step function jumps at each detected value, and then fitting the proportion of data to the left, as it's shown here, the left of these blue lines, which are the 4 detection limits. So how do you choose which distribution to fit? Well, we'll try several of them and use some of those statistics that test to see which are best. And so the PPCC is the most commonly used one. So for here, I fit with this command. This is all in the env stats portion of R. Fit this, and the PPCC is 0.97 for a gamma distribution. For a log normal distribution is 966, that's pretty close. And another one that looks pretty close is the normal, 0.968. And I will just tell you that the PPCC doesn't do a good job of picking up with its method of computation the negatives, the negatives that you don't see in the detects. So it's not efficiently figuring out that the bottom end of this distribution is getting misfit. So I've seen this in a number of sets of data like this. So here, the best one would be the gamma, but the normal would appear to be just as good, 968 instead of 969 for this correlation coefficient. So I've put a star up here to say choose the best. You would not just choose the highest or the second highest or whatever PPCC if one of those is a normal. So what should you do? Let's suppose we decided that I'd really like to stick to a normal distribution because I've used that for years. And 968 looks just as high as 969. What you should do is go in and look at the proportion with some type of plot. Here we're back to the QQ plot. This has the linear scale of normal quantiles instead of percentiles down here. This has the arsenic concentrations on the y-axis. And see where the projected distribution, which is on a QQ plot, is going to be a straight line. Where does that dip below 0 if you're using a normal? And if it's any appreciable amount, in this, it looks like it's about 15% in this data set for arsenic, then you don't want to use the normal distribution because that percent of negatives is going to distort the estimated mean and variance and not give you good percentile estimates and not give you good UCL estimates either. So if you're going to choose a normal based on a numerical criterion, you need to back it up with plots. And if this line did not hit 0 until it was way down here, if 0 was much further down, then okay, fit a normal. But there are not many things that have a lower bound of 0 and where you're dealing with low values like non-detects that would not have an appreciable amount of values below 0, negative, if you fit a normal to it. So don't just use those numerical criteria, and that's particularly a problem with the PPCC criterion. I showed you an AD and Anderson-Darling before. There's also a BIC. That's a measure of fit. Another measure of error, and you want to make it small, and we'll see an example later on of that. So you can get all of those numeric criterion back out of the software as well. Okay, so this is the gamma QQ plot where the gamma distribution is plotted as a straight line. It was the highest PCC by just the third decimal place of 0.969. If we had used the BIC for the gamma, log normal, and normal, and again, that's a measure of error, so you want the smallest value, it's pretty clear that the normal is not as good as the gamma or log normal. So that's just, it is picking up, and the Anderson-Darling would be the same. It's picking up those negative values, projecting those as being something that's a downside. All right, so that is how you'd choose, is use a numerical criterion, but back it up with plots and make sure it makes sense to you. So I'm going to use the gamma. It was the highest PPCC and lowest BIC. Then in the software, it will fit that distribution, as I mentioned before, by maximum likelihood. This is the command in the env stats package to do that. It's a gamma distribution. Alt means it's going to give you the results back in the original concentration units, and it's doing this for censored data with Nondetects. I want to get back a mean. I want to get back a confidence interval that's an upper 95% confidence interval, so it will do all of that for you. It'll give you back an estimate of the mean and a coefficient of variation. And here's the UCL down here. So it's estimating a mean of 1.84 and the UCL at 2.57. And that would be about the best estimate you could come up with for this data set. You could compute percentiles. You're just getting the percentiles for the data. That's just a different command, but it does this in the same way. It's going to use the characteristics of that gamma distribution. And here is the 90th percentile of 4.05 and the 95th of 5.17. And you could compare those two percentile-based standards. You could compare the UCL to a mean-based standard, and you wanted a protective number where it would not occur very often. So all of that can be done. There is, since this is 21 observations, a non-parametric alternative. It's called Kaplan-Meier estimate, and you can bootstrap that. And so you could get back, this is not assuming any distribution. It's basically using that step function. It's using the shape of the data as they are observed to give you back an estimate of the mean and an estimate of the UCL, and they're very, very similar to what the gamma results were. So as you get a higher than 20 observations, you can start to do these kinds of things with confidence. That the idea here is you're not assuming a distribution, so you're assuming that the data that you have are covering even a range up to the high end and the low end. They're having a good representation of even the far out kind of observations that you might see. And depending on how far out you want to go, you would then be comfortable using a non-parametric method. And that would be my preference in that state. You don't have to assume anything. So this software will compute other distributions as well as a gamma, log normal, Weibull, and a whole bunch more. You can do it by other methods than maximum likelihood if you want. There's one, the robust ROS method, which is a little bit less sensitive to whether you've got the distribution wrong or not than MLE. If you'd like more information on all of this, I've already shown you the book that I wrote back in 2012, one by Steve Millard in 2013, which gives you a commentary on his env stats package for R, is very good in discussing how all of these methods work and when you might use them. There is with every package in R a free PDF guide to that package. So you can find that on the site that has R. Didn't want to go there yet. So that's on the CRAN site. And so the conclusions for today are that you don't want to simply assume a normal distribution for small data sets and compute t-intervals to get a UCL or a percentile, because the normal often does not fit data that have Nondetects. Why? Because those are things that usually cannot go below 0, and yet you're working right down close to 0. That's why you have Nondetects. So you're going to have skewness, and fitting a skewed distribution will give you much better results. The survival analysis version of QQ plots, the one that leaves spaces for all of the non-detects and correctly computes the percentiles, accounting for that necessary space. Those versions of the survival analysis QQ plots are much better to use, and they handle multiple detection limits. I gave you one example with a single detection limit, but they handle multiple limits. They're just going to stick in. It's like sticking in air pillows and holding the space. Then they'll give you some measures, numerical measures, to decide what's the most likely distribution, the best fitting distribution, and you can compute statistics and compare them to standards. Use the PPCC, or perhaps better, the BIC, or Anderson-Darling, AD statistic, to find the best fitting distribution. Oftentimes, software will have more than one of those. Minitab certainly has PPCC and the Anderson-Darling. I bet that you could get the BIC out of it, or at least the components that make up BIC. In R, all of these are possible to print out. So you'd pick the maximum PPCC or the minimum BIC and the minimum Anderson-Darling AD numerics to get the best fitting distribution. And so with that, I'm going to look at the questions that you have typed in and cover as many as I can. When you say N observations, do you mean the number of results which include non-detects? Yes, I do. Non-detects are real data. They are just small data, so small values. What does the PPCC stand for? It stands for the probability plot correlation coefficient test. Okay. And that's a standard test for how well data fit a distribution. And if the data fit the distribution well, or it's really more that the distribution fits the data well, your distribution is a theoretical construct, the data are real. So if the distribution fits the data well, the PPCC will be close to 1, close to a straight line on a probability plot. Does ProUCL generate QQ plots using survival analysis? I believe with version 5 they did implement that they have a QQ plot that leaves the space for the non-detects. So I believe starting with version 5, but not before they do that. All right. How well does the Shapiro-Wilks test work for fitting data with non-detects compared to the PPCC, BIC, and AD? Well, the Shapiro-Wilks, and there's a version of it, the Shapiro-Francia test, work fine if you're comparing something to a normal, but it's not expandable to the other distributions. At least that's my understanding. So that you'll only find that test, the Shapiro-Wilks test, when you're comparing data to a normal or some transform like a log normal. So to decide whether to use a normal or log normal, it would be helpful. But once you move into gamma and other Weibull distributions, those kinds of things, you would use one of the other three. So that's why you don't see it in those fitting kind of procedures very often. Okay, in the guidance from EPA somewhere, it says that if you have less than 20% sensor data, you can use the substitution method. Your comment? It depends on guidance. I know an EPA guidance that says if you have 5% or 10%, I forget which of those, you're in real trouble if you substitute values for data. So there's a lot of different guidance documents out there. I can tell you from 40 years of experience, as well as from simulation studies, that it doesn't take a lot of substitution to really destroy your estimates of the mean, or to do regression equations or other things that we would like to do. And that all of these methods that I'm showing you that do not do substitution have been around since the 1950s in many cases in software, just not in the software that you were taught in college, unfortunately. So these are far better. And I think that you'll find out in recent guidance documents, they are going to tell you not to do substitution. All right, why not report a geometric mean for log normal distributions rather than an arithmetic mean? That would be fine to do. A geometric mean will be an estimate of the median, not the mean, though, not the arithmetic mean. They are two different things. And so if your regulations have to do with a mean or a UCL 95, a geometric mean won't help you. So that's the main reason why people still are estimating means with skewed data. Do you have an example available for how to estimate the UCL 95 for data sets with fewer than 8 observations? That's a great question. No, I don't. Why do I not? Because I don't think it's really going to help you very much. I think if you have fewer than 8, your best estimate is, I need to collect some more data. And there are simulation studies that back that up. I think the variation in your estimate is going to be huge. So you need data to summarize data. That's the problem. Is the next webinar also for free? Yes, it will be. Okay, are the lnx and log10x both useful distributions to test for? They are really the same thing. So it will be a different scale in the terms of the numbers that are sitting up there, but in terms of the physical look of the scale and the results that you get back when you retransform them, assuming you retransform them correctly, raising 10 to a power for the base 10 logs and raising e to the power exponentiating for the base e logs, then you're going to get the same results back in the original units. So you could use either one. In some sense, it's a matter of taste. For the things we're talking about here today, it doesn't matter. Natural logs are a little bit easier when you're doing some math. So for things that I'm not talking about today, a natural log would be better to use just because it's easier, less complicated in the formulas. And math and statistics software is always going to use the natural log unless you tell it otherwise. There are functions that would be something like log10 or some other function in that software to get base 10 logs. But if you just type log, it's going to give you natural log. Okay, I'm familiar with the use of normal and log normal distributions, not as familiar with gamma. What type of environmental chemistry situations would gamma be more appropriate than log normal, etc.? A gamma is just another skewed distribution. There are people that like the gamma distribution best. There are people that like the log normal distribution best. I like the one that fits my data the best. And so I would use some statistic to decide which to use. If you do plots of the gamma and log normal, and you saw one earlier with the red curve and solid line for the gamma, and I believe it was a dashed green line for the log normal, they look pretty similar, and they are going to give you pretty similar results. Their biggest difference would probably be in the far upper end, where the log normal would tend to give you a greater probability of getting extreme values up in the upper end. Unless you have a lot of data, more than 20, far more than 20, it's probably going to be a hard sell. It's going to be hard to know whether you really should use a gamma or a log normal. So I would use the one that has a mathematical justification that it appears to be the best. Okay. And the log normal is used because we all are familiar with normal distributions and we're familiar with logarithms. So people in environmental science have used log normal for years. In the field that has developed all of these censored methods back to the 1950s, and that's medical statistics, they use a Weibull distribution as their go-to distribution. It's another skewed distribution, and it's not quite as skewed as either the gamma or log normal. Any of those three would be good bets for what would fit your data well. When comparing against standards that are well beyond the detection limit, is it the fit to distribution necessary? So when the standards are high above the detection limit, depends on what you're comparing to those standards. You still want to use the Nondetects to get an estimate of a mean or a UCL 95 or a 95th or 90th percentile, whatever is going to be compared to the standard. So If you're using a percentile, and we'll say this, if you're using an upper percentile so that it's the 90th or 95th percentile, that's up in the high range, as long as that's above the detection limit, then using the percentile with any placeholder for the non-detects, not throwing the non-detects away, but using some placeholder for them, would give you the same answer. And it'll give you the same answer as doing this. So when you're interested in the high upper end, then it may not matter a lot what you do with the non-detects. The reason to estimate distributions as opposed to just computing the sample 95th percentile is when you don't have a lot of data. To even compute a 95th percentile, you have to have 20 observations. Might be 19, I forget, one of the two. So if you don't have that number, then you're going to need to fit a distribution to fit a percentile that high. Do you have any suggestion on the relation between the percentage of non-detects and method substitute with 1/2 MLE ROS Kaplan-Meier to be used for the analysis? Yes, in a sense. If you put in 1/2 or any other function of the detection limit, you will be wrong. And so it's going to do terrible things. You notice that straight line of values. The problem with substitution is that you're doing it for more than one observation. And so you're putting a pattern into the data, a pattern on the plot, and a pattern for making judgments like what distribution, a pattern on an XY plot that you might do regression with. You're putting in straight lines, and the data are not going to be in those straight, flat, zero slope lines. So you're going to get wrong answers, and that's been shown in journal articles for the last 30 years. So you shouldn't be using them anymore. All right, besides 1/2 or other substitution, percentage of non-detects and the difference between MLE, ROS, Kaplan-Meier. I do have those. It's in the book, so you could take a look there. As you get more and more data, it doesn't really matter which of those you use. The MLE and well, it matters in this way. The MLE is a parametric method. We're fitting a distribution to the data. So you have to specify ahead of time, I'm going to fit a gamma, I'm going to fit a log normal. ROS is only partially parametric. It uses the detects in a non-parametric format and then adjusts for the non-detects in a parametric format. So it's partially parametric. That gives you some benefit in that if you don't get the distribution correct, then it doesn't hurt as much. And Kaplan-Meier is a fully non-parametric method. So in those, I did decide based on what it is you're trying to do and whether you can use a parametric method or not. Okay. As you get fewer and fewer data, there is some argument for using parametric methods because basically what you're trying to do is project beyond the range of where your data are. And you can't do that with a fully non-parametric method, Kaplan-Meier. They say it's a data-only procedure with non-parametric methods. There is no distribution that you're going to project. So you have to have more data. Okay. So with that, I'm going to end this. Again, I want to thank you for attending. I do want to remind you of the webinar next month, and you can sign up in the same way that you have this time. So it'll be announced in various places, including a newsletter on LinkedIn and various other places. All right, thank you for attending. Goodbye.